So what happens at the capillary bed? Well, of course, capillary exchange. So let me talk about that. So let's look at a capillary. Okay. And blood runs one way through a capillary. Okay, so if it's coming in this way, right, it's going to come in nutrient rich. It's going to come in oxygenated, and it's going to leave deoxygenated. And where does it come from? Well, basically it comes from the heart, right? It goes back there. So we know at the heart the pressure starts at 120 and then it dissipates as it goes through the systemic circulation. But when it gets to the the capillary bed, it's about 32 millimeters of mercury. Okay, so that's as it enters the capillary bed. As it enters the capillary bed, it's called hydrostatic pressure. Okay, and of course this is a capillary bed, so we have, it's a good color for tissues. So we've got some tissues down here, right? So little, whatever that is, tissue somewhere. Okay, and keep in mind, you know, in the blood vessel, we've got blood cells. Wonky blood cell there. And other stuff too. We know what's basically in blood. Okay, so we've got red blood cells. Okay, we've got plasma proteins. So those are blue things. And we've got, you know, maybe some white blood cells. Okay. So how does the capillary look? So I'm going to kind of erase this little line here. Because remember that capillaries, the walls of capillaries are made up of endothelium, which is simple squamous epithelium. And these are flat cells, nuclei in them. Now remember, they're just one cell layer thick, right? So we're talking about tissue exchange or capillary exchange to tissues. So what gets moved? So what moves? Okay, so the first thing we want to look at, it's going to move, running out of colors. Just pink. Okay, so well, one thing is going to be oxygen. Remember, this is oxygenated blood right here coming in. And oxygen goes right through. Oxygen goes right through and into tissues. And carbon dioxide will be, the concentration of that will be higher in the tissues and it will diffuse into the vessel. Okay, this is just diffusion. So it's going from an area of high concentration of oxygen to an area of lower concentration of oxygen. An area of higher concentration of carbon dioxide up to a lower concentration of carbon dioxide. So just diffusion. Other stuff that moves, as the blood comes in, that hydrostatic pressure creates a pressure. We know this blood is hitting the walls. And it's creating a pressure there, pushing the fluid against the walls. And as that happens, the fluid is pushed out. And all the way down, that fluid continues to be pushed out. Okay? And this is regular, this is just blood pressure. And as it moves across down the capillary where there's resistance, that number is going down. So at the end of the capillary bed, it's at about, I don't know, 17 millimeters of mercury or 15, something like that. So it goes down. So that's why these arrows get shorter and shorter as it goes down the capillary bed. But as it's pushing against the walls, it's pushing fluid out. And that's what those arrows mean. It's pushing fluid out. And then whatever kind of fits with it, maybe some ions that are small or whatever. So whatever comes with it, comes with it. That process is called filtration because it's not specific. It's just getting pushed out and whatever fits goes and whatever. In a capillary bed, that flow is called bulk flow. So that's basically the filtration of the water being pushed out or the fluid being pushed out, and then whatever goes with it, whatever fits goes. So, those, if it's ions or something like that, they'll maybe go in the tissue. There may be some water that'll go into the tissue, whatever. But as the fluid is being pushed out of the capillary, it would just kind of be sitting in the interstitial space here. So we can't have all the fluid coming out of the capillaries. So what happens? We need a counter pressure. Let's use green for that. No, let's not use green for that. Let's use dark blue for that. Okay, so there's a counter pressure, and it comes from these plasma proteins. And it brings the water back in to the vessel, all the way down. This pressure is called colloid osmotic pressure. And it's about, I think, 30 millimeters of mercury. And you can see these lines that I wrote here, put here, are all the same size. Because does osmotic pressure change going down the capillary? Well, no, it doesn't, because osmotic pressure comes from the fact that there are plasma proteins in here. So there's not really more plasma proteins over here than there are over here. It's pretty much the same flowing through. So that pressure stays the same, and it brings fluid, and that's what's happening here, back into the vessel. It attracts it back in there. That process is called reabsorption. Okay. All right, so bulk flow, write this out. So bulk flow is a function of hydrostatic pressure. It pushes water out. Pushes water out of the vessel. And again, it decreases as we go down the capillary. All right, so it creates a filtration. Again, the water, the fluid water is coming out plus whatever else will fit. So it's not specific, and that's why it's filtration. So there is a net filtration that happens here. And that net filtration over a 24-hour period is about 3 liters. So there's 3 liters left in the interstitial space each day. All right, osmosis, and we'll talk, I'm going to get back to that, but osmosis occurs from the pressure, osmotic pressure, and it pulls water back into the vessel. And it's attracted to the solutes, or the proteins. All right, and that's absorption or reabsorption, however you want to call that. There are other things in here that can be, that move. Okay, so let's say glucose. All right, and let's say glucose is a big molecule. So it may not be able to get through here. So it may be endocytosed into the cell and then exocytosed out. So in and then out. And then here it'll be endocytosed into the tissue. So endocytosis and exocytosis can also move things. Into the tissue from the capillary. So the last thing about this is the fact that there are 3 liters of fluid left in the interstitial space. If 3 liters were to stay there every day, we would just blow up like balloons. Okay, so there's got to be something that counters that, and there is. So there are capillaries that are with around these capillaries, are special kind of capillaries called lymphatics. And lymphatics take in that extra fluid and take it back to the heart. Okay, lymphatic capillaries are extremely permeable. They're more permeable than regular capillaries. They're the most permeable vessels are those lymphatic capillaries. They have these little doors on them, little flaps, and when fluid presses up against the flap, it opens up and fluid goes in. So the lymphatic capillaries take up the fluid and then anything else that's in there. So it kind of will pick up, maybe some bacterias. If some proteins somehow got out of the capillary, it could take that up and they'll take it back to the circulatory system. Maybe if there's inflammation or something there and some red blood cells get out, those can go back up. So it basically cleans up what's left and takes it back to the circulatory system. And the lymphatic system has little stops on the way that cleans it. So it cleans that fluid of getting rid of like bacteria and stuff that are in there. So I think that's about it for capillary exchange. So we'll talk about the lymphatic system next because we're going into that and the immune system. But once that fluid enters the lymphatic vessel, it is no longer blood. It is called lymph. And then it takes that lymph back to the heart and dumps it in there, and it can re-enter the circulatory system that way. All right, so that's basically capillary exchange. That's the end of this chapter, I think, basically. So we'll start on the next chapter.